I'm Rob Persons with Artesyn Embedded Technologies. Artesyn is a company that's been around essentially for 35 years, but various incarnations of us. We originally were a Motorola Computer Group through a variety of acquisitions back when I was with Motorola. We acquired Force Computers and some other key players in the embedded marketplace. In parallel, Artesyn, which was a company that was actually originally started as Huricon, also acquired some companies. We all combined as Emerson a few years ago and have recently, within the last few years, become our own entity known as Artesyn Embedded Computing. In fact, Artesyn is actually one of the names that we had from the past and was easy to own because we already owned it. Today we're going to talk a little bit about a program that's happening within the Navy called the Aegis Weapon System. And this was actually the most recent technical insertion for the hardware, the compute hardware for Aegis Weapon System, and how we, doing a kind of a partnership working with them, got to a point where they're actually able to adopt advanced TCA, which is one of the open standards that we support, along with VME and some of the others, into the next generation of Aegis Weapon System. We're kind of showing you some of the things, the problems we ran across, and some of the solutions we had to get to that point of actually being able to use advanced TCA and open standard inside Aegis. A typical refresh cycle for most military programs, in the case of Aegis, is typically about every 4 years. It depends on the complexity of the program itself. In this case, their normal refresh cycle takes about 4 years, so they're deploying on the previous generation of hardware while they're looking at the next generation, potentially. They definitely want to reuse as much as they can, but also with the constraints of what they're trying to accomplish within the program. In this case, the previous generations, well actually, several generations ago, they used VME, and it was actually our VME bus products that they had used for really the decision-making part of Aegis. Aegis is, I guess I should start off by saying, is the main kind of decision-making software on a cruiser or on a destroyer that's actually coordinating sensor data that's on a variety of different elements on the ship and other ships within the fleet, coordinating defense against missile attacks, against aircraft attacks, a variety of different attacks. And so that's what Aegis basically does. So we started this process back in 2013. They looked at a variety of different technologies. They looked at other bladed architectures, proprietary and open. They looked at VPX. They looked at thin servers. They looked at a variety of different things. And they really were trying to drive themselves to a truly open platform, excuse me. Originally, it was they had migrated from VME to IBM Blade Center. Blade Center was a nice bladed architecture, but for them, the problem was it wasn't open. So they wanted to start to get back to that kind of open environment that they had back when they were using VME. Some time ago, they actually separated the I/O piece of this application from the compute side. So they really, truly were the drivers of open architecture. This is a Navy term that really isolated the compute side of this application from the I/O side. And so they're just looking for high density computing types of opportunities. And so some of the reasons why they selected ATCA, what the original decision was, it was a bladed architecture, which is what they were trying to get back to. Had very good performance to space. They wanted to move to 40 gig networks. And advanced TCA, since it's all internally cabled, had a nice configuration for them. It's very cost competitive, has long life, and was an open architecture. They really didn't want to get down this path again where they were essentially trapped with one vendor to be able to supply any of the next generation products during the next technical insertions. During this process, obviously, there was a qual testing that had to be done. This is not hard mounted into the ship itself. There's a shock isolated rack that's involved, which originally everybody thought that traditional enterprise class products that were NEBS would probably do fairly well in this kind of environment. As it turns out, NEBS is not the mill level of even in a shock isolated rack. And we noticed that primarily it's the vibration was the most difficult part for us to deal with when we were actually doing testing. We did initial qual testing when they originally had made the decision about advanced TCA, but they only looked at one axis. They only looked at probably the easiest axis, which is Z. They were concerned the most about shock as opposed to looking at what vibration might have an effect. And in turn, Shock was probably the easiest part of the testing to actually succeed with. Vibration was the hardest part. And it's the long duration resonance frequency vibration testing that they were doing. You can see there in the, actually it was y-axis, which is what they tested, and that was the easiest. Z-axis was really the worst. Looking at Z vibration at 2.5 Gs, really gave the chassis, the backplane, the boards, the most kind of motion that they could, that started to see some real problems. So we had to actually go and start to make some modifications to the chassis to be able to survive this endurance testing that they were doing. They were doing a blade center before, so the blade center is a little bit weirder. It isn't a standard size. It's like about this tall, about 1.2 pitch, I think, but really long. So the dynamics were very different on this thing than the advanced TCA system. First thing, we were actually able to very quickly duplicate the problems that they were seeing. First thought was just let's get some motion out of the system. The backplanes were obviously quite, if you've ever dealt with an advanced TCA backplane, they're pretty thick. So we didn't think there was a huge amount of motion in that. We thought a lot of it may be due to the fact that the sheet metal in the chassis itself might be giving us too much flex. So you can see a variety of different stiffenings that we did on the side, the back. Again, we're not trying to dramatically change this chassis. We might have considered looking at a redesign of the chassis if we had time, but the initial qual was so far along in the program, we didn't have enough time to go through and say, let's redesign this entire enclosure to be able to adapt to you, or have you look at third-party sources for this enclosure. So we really needed to get this enclosure passed. We had made some special modifications to the top and the bottom to allow them to be able to rack this thing inside their shock isolated enclosure. So we really wanted to get that working. First steps were trying to look at stiffening, and it wasn't completely successful. We still saw some data drop. Next thing that we started to do was to work towards physically attaching the payload boards and the RTMs. There's only a couple RTMs that they use for the switches, but actually physically attaching them to the backplane. So we actually modified the alignment blocks that you normally see in advanced TCA, which typically has 2 pins. We removed one of those pins and actually put a screw hole on it and used a screwing mechanism to screw it to the backplane itself. Each of so you can show kind of an example of what the block was. What this allowed us to do is to maintain the existing board. It allowed us to be able to keep the Navy's need for being able to add potentially third-party vendor product in here. We're really just changing one aspect of advanced TCA, which was the alignment block. And it actually allowed us to be able to really do a nice job of tightly coupling these boards actually to the backplane. Along with this, we had a strong concern about serviceability. They had to be able to maintain these things out when they're deployed. So we are actually doing a variety of different capture screw mechanisms to go and make it easy for the techs to actually attach, detach the boards, do that sort of thing. So the final solution ended up being strengthening the enclosure, attaching those payload boards to the backplane, attaching the RTMs to the payload boards, basically getting everything locked down inside the standard chassis. The attachment points are modifications from the original standard, but not so severe that it kept other third-party vendors' products from being inside this thing, potentially in the future. And there was a plan to reuse the same enclosure for the next technical refresh cycle as well. So their long-term goal is to get at least 8 years out of this kind of technology today, with the ability to be able to migrate to newer and newer server technologies as time goes on. And that's what advanced TCA will give you. Again, third-party products will be easily modified for this chassis. And again, we're maintaining that critical piece of what one of the decisions they made, or one of the reasons they made the decision to move to advanced TCA was to maintain that openness to the system. And we completed shock and vibe a couple months ago, and we're moving towards production this year.